Ever wonder how your phone's AR app knows where to place a virtual dinosaur in your living room? Or how a self-driving car avoids crashing into a pedestrian? It's all thanks to SLAM, short for Simultaneous Localization and Mapping. Think of it as a robot's inner GPS. But instead of relying on satellites, it uses sensors to build a map of its surroundings while figuring out where it is in real time. But here's the catch. Noise, moving objects, and messy environments can throw even the best SLAM systems off track. Today, we're diving into a game-changing approach called ADA-DPM, which tackles these challenges head-on. Let's break it down, and trust me, it's way more exciting than it sounds. So how do traditional SLAM systems work? They rely on LiDAR, a laser sensor that creates a 3D point cloud of the environment. But here's the problem. Dynamic objects like cars or people and noise, think random sensor errors, can mess up the mapping. Imagine trying to navigate a crowded room while someone keeps bumping into you. Your mental map would get all jumbled. That's where ADA-DPM shines. It's like giving your robot a smarter pair of eyes. Let's look at its 3 key innovations. 1. Dynamic Segmentation Head, the Don't Trust the Moving Stuff module. This part of the system acts like a detective, figuring out which points in the LiDAR data are from moving objects, like a passing car, versus static structures, like a wall. By filtering out the dynamic ones, it prevents the robot from getting confused by things that aren't part of the permanent environment. It's like telling your robot, ignore that squirrel running across the street, focus on the buildings. 2. Global Importance Scoring Module, prioritizing the important stuff. Not all points in a point cloud are equal. Some are noisy, others are just random clutter. This module assigns a score to each point, highlighting the ones that matter most for accurate mapping. It's like teaching your robot to focus on the key clues in a mystery, ignoring distractions like a leaf blowing in the wind. By doing this, ADA-DPM makes sure the robot's map stays clean and reliable. 3. GLI-GCN Module, seeing the big picture and the details. This part is all about context. It uses a neural network to analyze features at different scales. Think of it as looking at a tree up close, to see its leaves, and from far away to spot its shape. By combining these perspectives, the system becomes better at recognizing patterns, even in tricky situations like a foggy street or a tunnel with no texture. The results? ADA-DPM outperforms existing methods in accuracy and robustness, especially in noisy or dynamic environments. Ever wonder how self-driving cars or drones see the world in 3D? It all starts with something called point clouds, digital snapshots of environments made up of millions of dots. But here's the challenge. When these systems try to map their surroundings, especially in tricky places like winding roads or open fields, things can get messy. Enter ADA-DPM, a game-changing system that's rewriting the rules of 3D mapping. Let's break it down. Imagine a robot driving through a busy city. It needs to tell the difference between static things, like buildings, and moving ones, like cars. That's where the dynamic segmentation head comes in. Think of it as the robot's focus mode. It filters out moving distractions like passing cars so it can stay on track. But mapping isn't just about filtering noise. It's also about prioritizing what matters. That's where the important scoring head shines. This part assigns a score to every point in the data, highlighting the ones that help build a precise map. For example, it zooms in on sidewalks or building edges instead of random bushes. It's like giving the robot a magnifying glass to spot the details that make a map reliable. Now here's the real trick. ADA-DPM doesn't just rely on static data. It uses a module called GLI-GCN to handle tricky overlapping areas. When a robot loops back to a place it's already mapped, GLI-GCN compares multiple views of the environment to spot similarities, even if the data is a bit fuzzy. This makes the map more accurate, especially in complex scenes like city streets. So how does it stack up? On datasets like Semantic KITTI and KITTI 360, which simulate real-world driving, ADA-DPM outperforms competitors like KISS-ICP and SCILA-GOLOM. It's especially strong in long-range tasks, like mapping a 10,000-meter stretch of road, where other systems start to falter. And here's a cool twist. It uses 60% less memory than alternatives, making it faster and more efficient for real-time applications. But the real test? How does it handle chaos? Researchers did ablation studies, removing parts of the system to see what's essential. Turns out each component matters. The dynamic head cuts out noise, the important scoring ensures accuracy, and GLI-GCN fixes those tricky overlaps. Even when 50% of the data was corrupted with random noise, ADA-DPM still built a reliable map, proof of its resilience. So what's the takeaway? Innovation in 3D mapping is a balancing act. Tools like GLI-GCN push boundaries, but they're not magic bullets. Real-world challenges, like sparse data or unpredictable environments, keep engineers busy refining their approaches. The next time you see a robot navigating a complex space, remember, it's not just about seeing the world, but understanding it in ways we're still learning to perfect. Thanks for watching. If you want to dive deeper into how these systems work, hit subscribe. And let me know in the comments, what's one thing you'd like to see explored next? Stay curious, and I'll catch you in the next video.